Okay, so we're going to talk about some examples of volume using the disk method. So we're going to find the volumes generated by revolving the bounded region around the given axis. So we'll do this once around the x-axis and once around the y-axis, just to get a good sense of it. Now, this is an examples video, so I'm just going to plow through a few examples. If you are looking for like a how-to with this method, like you really don't understand it, I would suggest watching my lesson video where I really break down the nuts and bolts of this, and this is just extra examples to go with the lesson video. So just a warning there. Okay, so I've got this region, so y equals secant x equals negative pi over 4, x equals pi over 4, and I'm rotating this region now around the x-axis. So hopefully I'm a broken record about this, but you really can't do this if you don't have the sketch. So first things first, I want to plug in these bounds here into this function. So I'm just going to set up a graph and plot those points. Okay, so just a few reminders if you're like, secant. So secant is 1 over cosine x. So really, if I know the value of cosine of pi over 4, which is square root of 2 over 2, then if I take 1 over that, oops, I'm sorry, this should have been a 4, not a 2. 4, 1 over cosine pi over 4. That's just going to then be the reciprocal, right? So now it's 2 over the square root of 2. And then I can just rationalize the denominator to get that this is actually just equal to the square root of 2. Okay, so I've plotted the points negative pi over 4 and pi over 4 both at the square root of 2 because both of these are going to end up just being the same y value. So now that I know that, I can draw out the rest of the sketch. So I am familiar with what the graph of secant looks like. So I know that this is just a portion of the graph. So it's really helpful to have like a little reference sheet of all these base graphs so that you have some semblance of an idea of just like how this curve is going to flow. Okay, so that was just for secant x, and then I have negative pi over 4 and pi over 4, so those are those lines there. So the region that we're referring to is this bounded region here. And I always think it's a good idea just to sketch out what the solid looks like, because that just kind of reiterates the whole point of this. So we're finding the volume of something that looks like this, okay? So we rotate it around the x-axis. Okay, so now I can bust out the formula for the disk method, which I think is nice and straightforward. So I'm just really going to take pi r squared, right, where r is going to be, well, whatever the radius that's being generated kind of by this curve here. And this curve would be secant x. So this really just comes out to being pi times secant x squared. And then I can take the pi out. So this is a nice integral to work with. We have a nice antiderivative formula. So this one is kind of one of the easy peasy ones. So I'll just give myself a little more space. So the antiderivative of secant squared is tangent x. And then I can just plug in my limits of integration. And I've got the work here if you want to hit pause. But what I got is that this comes out to 2 pi. Okay, so now let's take a look at something maybe a little bit harder. So I've got x equals 2 over the square root of y plus 1, and then x equals 0, y equals 0, y equals 3, and we're revolving this around the y-axis. Okay, so if you're watching this, I'm assuming that you're struggling a little bit with these types of problems, and you don't get better at this if you don't try. That's really the key to calculus. So I'm going to give you a big hint if you're like freaking out on how to draw the graph. Start with these y values. So plug these points into the function and plot those points to start your sketch. I would rather you draw a wrong sketch than no sketch and just watch me do the example. So I suggest you pause here, hit play when you're ready. All right, so I plug in y equals 0. At y equals 0, this just becomes 2 over 1. So here's y equals 0, and then x will end up being 2. And then at y equals 3, so if I plug that in, this becomes 2 over the square root of 4. So 2 divided by 2 is 1, so that x value is 1. So here's y equals 3, here's x equals 1. Okay, so, all right, so, you know, it's going to act kind of like a rational function, so I know it's going to probably connect something like this and maybe be a little bit curved. So I know just a little bit about how rational functions tend to work, and so then I can kind of rely on this. Now, if you were really nervous and you were like, I wasn't sure that this was the graph, the easy way to resolve that is to just choose another point in between just to give you some confidence of what your shape looks like. So you just really need like this basic sketch, and a couple of points can go a long way with figuring out the sketch. So, okay, that's the first part of the sketch. So now I really want to recommend that you pause the video and you try to finish the sketch and draw what the solid looks like before we go on. So pause here, hit play. Okay, so remember, I've got x equals 0, y equals 0, and y equals 3. So here's the region that we're revolving around the y-axis. So we've got something that looks like this. All right. So since I'm going around the y-axis, now I just need to have my function everything in terms of y. So I just need to find, so this like pi r squared formula, except now I need this function in terms of y, which, you know, our function is in terms of y, and this whole radius is really being dictated by this curve anyways. Okay, so all I have to do then is plug in that function, bada bing, bada boom. All right, so let's make a little space. I bring the pi out and I square this function. So this just comes out to be then y, or 4 over y plus 1. Okay, and so now sometimes when you get to this point, you still have to do some fancy tricks with your integrating. So in this case, I can't integrate this as is. I've got to use substitution. And so in this case, I've got my y, or my u is going to be y plus 1. My du is going to be just dy. And then I'm going to change my limits of integration. So if y equals 0, if I plug that in, 0 plus 1 is just 1, so u is 1. If y equals 3, 3 plus 1 is 4, so u will be 4. So now I can finish this. And I strongly recommend, if you're a little shaky on the integration, you finish this on your own and then hit play. So now I'm just left with this integral here, and I brought the 4, see, I brought the 4 out here, so now I've just got 1 over u. And to integrate 1 over u, so that's just going to be the natural log of u, and then I can just plug in my limits of integration so you can see the rest of my work here. So the last thing I want to mention here, so I've got 4 pi times the natural log of 4 minus the natural log of 1. Natural log of 1 just equals 0, so here's my final answer. Okay, and so that's it for that. Consider giving this a like if you found this helpful. I always really appreciate that. I'll catch you guys in another video.